All right, welcome back. So there's a second handout that'll be coming around this week, and this is this handout of registers, which will help you with interrupts and also with timers, and with pulse width modulation and A to D conversion and all this other stuff we're going to be doing the second half of the course. So timer 0 is basically controlled, or basically interacts through two registers, T0 configuration and timer 0. Okay, and timer 0, as usual, being possibly a 16-bit register, has two pieces, timer 0 high and timer 0 low. Because it's a file register, but file registers are always 8 bits. So when we talk about timer 0, we're really thinking of the 16-bit register comprised of timer 0L concatenated with timer 0 high, the low byte and the high byte. But let's look at T0 con, the control register. So here's a picture of T0 con, right? T0 con is just a special function register. Don't worry about where it is. If you use the include file, T0 con will be defined as a symbol, and it'll be the correct file register address of this register. All right, so bit 7 is easy. That turns the timer on and off. If you want to use the timer, set bit 7 to a 1. If we ignore the other bits for now, right, then we turn the timer on. Timer 0, the register, right, these two registers will start incrementing every 8,000th of a second. It's going to increment. When it overflows, we'll get an interrupt request. Okay? But that's the simplest view of what's happening. So each instruction, so the instruction clock is an 8,000th of a second. And in the simplest version, every time that the instruction clock ticks, timer 0 gets incremented. Okay, but since this clock is going pretty fast, 8,000 ticks per second, and a 16-bit register is about 64,000, the longest we could possibly time would be about an 8-second interval. Because if we wanted to wait 10 seconds, we would need to arrange for this register to overflow after 80,000 ticks. Well, we know that whatever value we put into a 16-bit register after 65,000 ticks, it's going to overflow. So if we just use the instruction clock to increment timer 0, we wouldn't be able to get a very long timing interval. So there are ways to divide down this clock to say, let's not use every tick, let's use every other tick. So we'll use this tick, and this tick, and this tick, but we'll ignore the ones in between. So 1/8,000th of a second, timer 0 increments. Next 8,000th, nothing happens. Next 8,000th, timer 0 increments again. Nothing happens, timer 0 increments. By doing this, if you think about it, you'll see that what's happening is we're effectively slowing down the clock. We're saying let's only increment every 4,000th of a second, or every 2 8,000ths of a second. Well, if it's incrementing 4,000 times a second and we want to wait 10 seconds, that's easy. Just set a value that will overflow after it ticks 40,000 times. So by being able to scale the way that we're incrementing timer 0, instead of just using a straight instruction clock, we can get longer timing intervals. Okay, so the way we do this is by using something called a prescaler. And to use a prescaler, we have to do two things. One, we have to set bit 3 of this register to a 0. That says we are using a prescaler. If we set this bit to a 1, there's no prescaler, and it's purely what we've been saying. One instruction tick means increment timer 0 by 1. But if we set this bit to a 0, then we can specify how much we want to scale down that instruction clock. So these 3 bits, bits 0 through 2, are coded to indicate what our prescaler should be, everything from 1 to 2 to 1 to 256. So what does that mean? Well, this is a 1 to 2 prescaler. Okay, basically it means that you need 2 instruction clock ticks before we increment timer 0 once. Now, if this is our instruction clock, and we set a prescaler of 1 to 4, it means we need 1, 2, 3, 4. 2, 3, 4. We need 4 ticks of the instruction clock before we increment T0, before we increment timer 0 once. So 1 to 4 means 4 instructions equal 1 increment of timer 0. So you can imagine if we set the prescaler to 1 to 256, what does this mean? 256 instructions equals 1 increment of timer 0. So after 256 8,000ths of a second, timer 0 will only get incremented by 1. So we can get a very long timing interval like this, right? What's the longest timing interval that we can get? Initialize timer 0 to 0. It's going to take 65,000 ticks before that overflows. And if a tick is only happening every 256 instructions, that's going to take 65,000 times 256 instructions. And we've only got 8,000 instructions a second. That's a very long timing interval. Okay, that's getting up to be a good fraction of an hour. So the prescaler is a way that we basically slow down the rate at which the timer 0 register gets incremented relative to the instruction clock. Okay, so a few other details in here, most of which we don't have to worry about. We don't need to use the instruction cycle clock. We can actually tick this timer using an external pin. Okay, we're not going to do that in this course. So bit 5 will always be a 0, which says do what we've been talking about, use the instruction cycle clock as the basic source. If we were using an external pin, we can say, do we want to increment on the high or low edge? That doesn't matter to us. Okay, this assigns the prescaler or turns it off. This is the prescaler value. That leaves us with bit 6. So bit 6 is kind of quirky. We can say, do we want timer 0, the register, to be 8 bits or 16 bits? If we make it 8 bits, then we're only using this timer 0L bit. Okay? There's no reason not to use 16 bits, but the arithmetic is a little easier if you use 8 bits. And you just need a short timing interval, because in this case, timer 0 will increment until it gets to 255, and then on the next tick, it will overflow, and that's where the interrupt request will occur. Alright, so it's a combination of do we want 8 bits or 16 bits? What should we initialize timer 0 to? Should we have a prescaler? And if we have a prescaler, what should that prescaler value be? And the understanding of what the system clock is, 32K, which gets divided by 4, which gives us an instruction clock of 8K. Okay, this is in the book, this is in the data sheet, but that's a sort of pared down description of how this subsystem is working. And you can read a little bit about this in here, but it's very verbose. All right, so what about the interrupt piece? When timer 0 overflows, it will request an interrupt. But that interrupt has to be enabled, and it's enabled in the intcon register, and it's this bit over here, timer 0 interrupt enabled, bit 5. If we set that to a 1, and if we've enabled interrupts with bits 6 and 7, then when the overflow occurs, we'll get a request to the interrupt subsystem, and we'll jump to location 8 to process the interrupt. And once we're processing the interrupt, we can check this int 0 interrupt flag to see if it was timer 0 that caused the interrupt. Right? So every interrupt has an enable bit, and it has a flag bit. There's timer 0 enable, there's timer 0 flag, there's int 0 enable, there's int 0 flag. And since all of our high priority interrupts will take us to the same location in our program, location 8, we need a way to know, hey, why are we here? What interrupted us? So we can check these interrupt flags to know exactly what the cause of the interrupt was. All right. So that's a little more detail. That's a lot more detail, actually. Playing with the timer subsystem in the simulator is a little tricky because you don't want to step through thousands of instructions to simulate the behavior of the timer overflowing. So timers are good to play with the actual chip itself. Try to set up something that'll toggle an LED every half second by using the timing subsystem. We're going to work on the board, and we're going to go through some homework problems that look at setting up these timer registers in different ways, conditioning the interrupt system, and so on and so forth. Let me point out one more thing, and then I'm done talking today. When we do a 16-bit version of timer 0, we need to be very careful about how we write timer 0 high and timer 0 low. Okay? What we want to do is we want to write the high bit first and then write the low bit. This is important. Okay? Sorry. Scratch that. Nope, that's right. So we want to write the high byte first, and then we want to write the low byte. And what's happening is when you write the low byte, that actually causes your write to the high byte to take effect. Okay? So when you want to write, let me put this on a separate sheet. When you want to write to timer 0, write the high byte first, and then write the low byte. When you want to read, we want to do something different. We want to read the low byte first, and then the high byte. And this is subtle, but it's important. And it would take an entire lecture tape just to kind of explain why we have to do things in this order. But we can talk about it another day in person if you're interested. But you can just kind of take it as a given when we're working with timer 0, high and low. Right? When you're writing values to here, write the high byte first and then the low byte. When you're reading, read the low byte first and then read the high byte. All right, that's all I got for now. I will see you in class.